exponential growth function. So our objective for this lesson is going to be to write, graph, and analyze exponential growth functions. So our functions today are going to grow or get bigger, but they're going to do so exponentially. So we need to talk about what does that mean. Okay, so in general, an exponential function can be expressed in the form a times b to the x, where a and b are real numbers, with a not equal to 0, b greater than 0, and b not equal to 1. Okay, so let's go ahead and let's talk. That's a lot going on in here. Okay, first of all, to notice on this exponential function, it's a times b to the x. The only thing with the exponent on it is the b. Okay, so the only thing with this exponent x is the b. Okay, so by order of operations, we have to take the exponent first and then multiply it times the a. Okay, so we take b to the x. Okay, the first thing, a cannot be 0. Well, if a was 0, so hypothetically, if a was 0, I'd have 0 times something to the x. Well, 0 times anything is just 0, and this would just be a 0 function. It'd be a mute point. It wouldn't do anything. It would just be 0, always 0. It would be a constant function. Okay, b has to be greater than 0. So that b, what we refer to that as the base of the exponent, the base has to be positive. For it to be a growth function and get bigger, the base has to be positive for it to grow. If the base is negative, it's not a growth function. We're just talking about our growth functions right now. So it has to be positive for it to grow. So for me to multiply positive numbers multiple times, it's going to get bigger. Well, if I'm multiplying negative numbers multiple times, it's going to give me way negative, so smaller. Okay. And this last one, b cannot be 1. Because if b is 1, I'd have a times 1 to the x. 1 to any power is just straight up 1. So then again, this would just be a constant function. It wouldn't grow. And here we're looking at growth functions. Okay, so growth functions. So this involves us knowing about exponents. B is what we call the base. X here again is what we call the exponent. So this is different than the exponents we've done in the past. In the past, our x has always been the base. Now our x is not the base. Now our x is in that exponent. Okay, so the input is the exponent. Okay, so to be able to evaluate those, we need to know some of our exponent rules from way, way back when, earlier in the year. So first we have to talk about, what does a negative exponent do? A negative exponent takes the, oh, I don't want to use red, that looks angry, takes the reciprocal. Okay, so if you remember a negative exponent, like an exponent of negative b, will give me 1 over a to the b. It takes the reciprocal, it moves it to the denominator. So if I have 5 to the negative 2, that would be 1 over 5 to the second, which is 1 over 25. Okay, so that exponent, that negative exponent, takes the reciprocal. Okay, a zero exponent is always equal to 1. Anything to the 0 power, 6 to the 0 power is 1. 1/3 to the 0 power is 1. Negative 576 to the 0 power is 1. Anything to the 0 power is 1. Okay, so now rational exponents. Again, the word rational, whenever you see the word rational, I want you to think fraction. So now fraction exponents, if I have a to the 1 over b, that means I have the b root of a. So if I have 4 to the 1/2, that means I have the square root of 4. If I have 27 to the 1/3, that means I have the third root of 27. And often for our fraction exponents, when just dealing with exponential functions, we'll use our calculator to get us some good approximates. These we don't need. The square root of 4 is 2. The cube root of 27 is 3, because 3 to the third is 27, because 2 to the second is 4. So that leads us back to, so those are the review of our exponent rules, because we're going to need them. Okay, so here we're going to look at this exponential function, f of x equals 2 to the x. And we are going to create a table of values. so we can graph this guy. Okay, so here's my input x. My output is my f of x. And it's going to be 2 to the x. So let's go ahead and let's just pick some nice numbers. Let's pick, I always like to start with 0. 2 to the 0. Anything to the 0 power is 1. What about 1? 2 to the 1 is 2. 2 to the second is 4. 3, 2 to the third is 8. 4, 2 to the fourth, multiply by 2 one more time, 16. Okay, so let's go ahead and let's get these points into a graph. Oh, let's graph these guys up. That's a little low, but that's all right. So we would have the point 0, 1, 0, 1, point 1, 2. Okay, that looks pretty good. Have the point 2, 4, 2. All right, now that whole slope thing, as you can tell, this doesn't have a constant slope. If I connect these dots into a line, that has a slope of 1, but these dots has a slope of 2. We have the point 3, 8. 3, 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's even steeper yet. Have the point 4, 16. Okay, which now we're going to be off the graph. There's 8, 9, 10, 11, 12, 14, 15, 16. So this gets really big really fast. I mean, I haven't even put in, like, what if I just put in a 10? 2 to the 10th. That's multiplying 2 10 times. I'm going to grab my calculator. Type in the 2. The button is right above the divide button. There's that little up arrow. That little up arrow gets me, it's called a caret. It gets me up into the exponent. So 2 to the 10th is 1,024. Okay, so 2 to the 10th is 1,024. And that's just a base of 2. Okay, I'm just multiplying 2 10 times. Imagine if I was multiplying 16 21 times. It'd be huge, huge, huge. Exponential functions grow really fast. Okay, so let's go ahead and let's try, we haven't done any negatives. Let's try like a -1. 2 to the -1 would be 1 over 2 to the 1, which would be 1/2. So we'd have the point -1, 1/2. So -1, 1/2. Okay, -2. 2 to the -2 be 1 over 2 to the second, which would be 1/4. So we'd have -2, 1/4. 1, -2, 1/4. Okay. What about -3? We'd have 2 to the -3, which would be 1 over 2 to the third, 1/8. So we'd have the point -3, 1/8. You see, I'm just getting smaller and smaller and smaller fractions. And as I go, I'm just going to keep getting smaller and smaller and smaller fractions. I'm never actually going to get a negative because the negative exponent takes the reciprocal. So I'm never actually going to get a negative. So my graph ends up looking kind of like that. I'll pretend I hit those a little bit better. Okay, but it never actually goes negative. I never actually go down here at all. There's no way, and if you think about it, it makes sense. If I'm taking 2, if I'm multiplying the number 2 a certain number of times, is there any way for me to get a negative number? Nope. Okay, so we don't go down into those negatives. Okay. So again, this is our exponential growth function, because if you notice, as I go from left to right, this function grows, and it starts growing really, really small, itty, bitty, bitty. But as I go, it grows really, really big, really, really fast, okay, as we travel to the right. Okay, so there is our exponential growth function. It is only an exponential growth function, so here's our just exponential function in general, a times b to the x. If a is positive, a has to be greater than 0. A has to be positive, and b, my b has to be greater than 1. My base has to be larger than 1, so bigger than 1 for it to be a growth function. If that b is smaller than 1, like 1/2 or 1/3, or we know it can't go negative, and we discussed that up here, we know it can't go negative. It has to be bigger than 1 for it to have that growth. So here we're looking at 3 exponential growth functions, all with different bases. The first one is 2 to the x, the second one is 3 to the x, and this last one here is 4 to the x. And then here's the graphs of them. If you notice, all the graphs look very similar. Very, very similar. What is the y-intercept for each of the graphs? So if we come in and look, the y-intercept for this one, and this one, they look all about the same. The y-intercept occurs when x is 0. So 2 to the 0 is 1. 3 to the 0 is 1. 4 to the 0 is 1. Oh, they all have the same y-intercept. They are all 1. And I hope you notice that they're always going to be 1 if it's just a strictly 2 to the x kind of situation. No matter what your base is, okay, that y-intercept's all going to be 1. Do any of the graphs have an x-intercept? Do they ever cross this line? It looks like they get really, really close, but they never actually cross. There is no x-intercept because they are never going to go down here into negative land. So there is no x-intercept. They never actually cross it. There's no way I can multiply 2. There's no way I can multiply 2 a certain number of times and ever get an actual 0. I can get really close to 0. I can get really, really close to 0. If I take 2 to the negative 100, that's going to be 1 over 2 to the 100th, which, okay, 2 to the 100th, let's just go 2 to the 100, is, okay, 1.2 e to the 30. Okay, what that means, this is what the calculator get, 1.2 and a bunch of stuff, e to the 30. That is 1.2 times 10 to the 30th. So that means there are 30 zeros behind here. There are 30 places. So this is like a 1, 2, followed by like 30 zeros. So it's huge. It's huge, but it's not quite 0, okay? It's just a really, 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 really tiny, tiny fraction, infinitesimally small. Okay, so one thing to keep in mind is if I actually type in 2 to the negative 100, okay, there, it gives me that really small number. Your calculator has like, if I get too small, your calculator and many times will actually give you 0. But really, it's just a rounding error. Okay, so there, it gave me 0. It's not actually 0. It's just such a small number that the calculator just rounds it to 0 because it is so infinitesimally tiny. Okay, so no, they do not have an x-intercept. There's no way to actually get to 0. You get really close, but not actually get there. So what appears to be true about the domain and range? So your domain is those input values. Okay, inputs or your x's. Okay, if I look at my x values are the left and right. There is a value for every single left and right. The domain is all real numbers. I can put any number. So again, we write that as that fancy R, all real numbers. The domain is all real numbers because this goes left to right for forever. This goes left for forever. This goes right for forever. It has no holes anywhere in the graph where there's certain x values that are skipped. It has no like big gaps, like there's no x's for in between here and here. There's none of that. So that domain is all real numbers. Okay, the range on the other hand. If we look at the range is that output or those y values. Hey, well, we talked about it up here. You don't ever go down here. We never go down into the negatives. We only go from 0 on up. So the range, again, is my output, or my y is my up and down. And my function basically starts here at 0 and goes up. So my range, my y values, are going to be bigger than 0. Or we would write it as my f of x is bigger than 0. And we just talked about how we can't actually equal 0. So my f of x is greater than 0. So we're just talking about positive range values. And that's true for all of them. All of these go from 0 on up. Hey, none of them ever go down here. There's nothing down there for any of them. So they all have a domain of all real numbers. They all have a f of x greater than 0. What happens to the value of the function? Okay, the value of the function, that's that output value. As the value of x increases without bound. So as x gets really big, this is just asking, as x gets really big, what happens to my y? So as x gets really big, that would be going this way. As x gets really big, this goes up really big too. So as my x gets really big, my value f of x also gets really big. Okay. The function also increases without bound. I could also use those same words. I could also say it increases without bound. The function also gets really big. As I put really big numbers in, okay, as I 2 to the 100, 2 to the 200, as I put those really big numbers in, yeah, my output's going to be really big too. Okay. So what happens to the value of the function as the value of x decreases without bound? We just talked about this. As we get really small, as I put super, super negative numbers in, what does my function do? It gets really, really small, but not negative. It actually gets really, really close to 0. F of x gets really close to 0. So one way we'd write it is we say f of x, we do an arrow for approaches 0. F of x approaches 0. We wouldn't say it gets really, really small because it doesn't actually go negative. And we can get smaller than 0 by going negative. But it gets really, really close to 0. Like, as we talked about here, as I put in like a negative 100, I get really, really small. I get really, really close to 0. What is the value of the base b for each of the functions? Okay, well, looking here, the base b, the base on this first guy is 2, the base on this guy is 3, the base on this guy is 4. For which value b does the function increase the most rapidly? So which one of these actually has it going up the fastest? This one, or this one? Which one has the steepest curve? Yeah, this one. The base of 4. The base of 4. And it makes sense. As the base gets bigger, as the number you're multiplying gets bigger, it's going to get bigger faster. Okay? Right, so we have a new vocabulary word, asymptote. An asymptote is a line, so it's a line, that a graph gets closer to as the value of x increases or decreases without bound. Okay, the standard asymptote for a exponential function is this 0. Here's the asymptote for all three of these. I'm going to draw it in big, bold, and red. There's my asymptote. My asymptote ends up being, in this case, y equals 0. Oh, let's make that a little bit smaller, like yelling it. Okay, y equals 0, in this case, is our asymptote. It's that line that it doesn't actually ever cross. It gets really, really, really close to. The graph gets closer to it as your x increases. In this case, it's as your x decreases, because as we go to the left, I get really, really close to that line. Okay. All right, so now we're going to look at, so far we've just been looking at a base to an exponent. We're going to look at what happens when I multiply that by a number. So here we have the graph of f of x equals 2 to the x. So now we're going to look at 3 times 2 to the x. So let's go ahead and let's create a table of value, and we're going to graph it on this graph as well, x and g of x. So again, this graph has just 2 to the x on it. Okay, we're going to graph this 3 times 2 to the x on it and see what happens. So let's go ahead, let's put in our 0. So we'd have 3 times 2 to the 0. Anything to the 0 is 1, so I get 3. Get the point, 0, 3. The other one was 0, 1, so now I'm 0, 3. Going to be right here. Okay. So what about 1? 3 times 2 to the 1. 2 to the 1 is 2. 3 times 2 is 6. So I have the point 1, 6, which will put me like right here. Okay, 3 times 2 to the second. That would be what? 3 times 4, 12. So 2, 12. 3 times 2 to the third. That would be 3 times 8, 24. 324. 4, 3 times 2 to the fourth. 3 times 2 to the fourth is 16. 3 times 16, I don't know. 3 times 2 to the fourth, 48. So 4, 48. Wow, a big 48 right here. Okay, and we can try, let's do -1. 3 times 2 to the -1. That would be 3 times 1/2, 1 over 2. So 3/2. Okay, so -1, I would be 3/2, which is going to be, oh, super small, 1.5, like here. And I'm still going to keep getting super small numbers. So even smaller. So really, we look like this. Okay, so if we compare, and we can grab our graphing calculator and we can graph them both. Okay, 2 to the x, 3 times 2 to the x, and I'm going to go right away a zoom 6 for a standard screen. Okay, so there's my 2. There's my 2 functions. If you notice, they're very similar. The red one, they're super similar out here. Like they're just both really, really small as we trace out there. But here, basically, we have 1 and then a y-intercept of 3. And then they're going to get bigger as we go out that way. And that 1 is always going to be about 3 times bigger, which we would expect as we go out. It's going to be 3 times larger. What changes do you notice? Do we notice any changes with domain and range? Nope. Domain and range are the same. It still goes left and right for forever. For up and down, it still goes from 0 on up. So domain and range are the same. It may grow faster. Okay, so like 3 times 2 to the x grows faster as we go out. 3 times faster to be exact, and grows faster, and it also has a different y-intercept. The first one had a y-intercept of 1. This one's got a y-intercept of 3. So that multiplying by that 2 really just made it grow a little faster and made the y-intercept a little different. Okay, so here is what's considered like the most standard exponential growth model. Okay, so when we have things increasing, R is that rate of increase. In many times, it's a percent. So we'll say usually a percent. But when you put it in the equation, you don't put it in as a percent. So let's say I know something's growing at a rate of 3%. Okay, I need to put that as a decimal first. That would be 0.03, because this means 3 per 100. All that percent means is it's a shortcut way of saying per 100. So if I say 5%, that means 5 out of every 100. That's all percent is a shortcut for meaning out of 100. So 3 out of 100, which 3 divided by 100 is 0.03, 3 in the hundredths place. Okay, so my rate of increase would be that, usually a decimal, unless you're increasing by a lot. Okay, A is usually that starting amount, what you're starting with. If it's an investment problem, how much are you investing? If it's a cell problem, how many cells are there to start? So forth and so on. Okay, so let's just apply this problem now here to a investment problem. So we have a new investment account is opened with $4,000 at the, so this is my starting amount. So this would be my A, 4,000. At the interest rate shown, this here would be my rate, or my R, which is 4.5%, which is 4.5 per 100, which 4.5 per 100, I would take, well, let's go out of there, 4.5 per 100, which would be 0.045 as a decimal. Okay, 0.045. If no additional money is invested, what will be the value of the investment after 5 years? So this is my input. This is my X. I'm inputting 5 years. Okay, so we didn't talk about that. This X, there's your input right there. There's your input, and that's the amount of time, or how long ago. So that input is normally a time. How long are you leaving this? Is it 5 days? If it's a cell reproduction, then it would be 5 days. So you put 5 in there. Okay, so if my function, so basically I want to figure out what is f of 5. So let's just write our function first. F of x equals, my original amount is 4,000, 1 plus my rate, which is 0.045 to the x. There's my equation, 4,000 times 1. If I add 1 in 0.045, I get 1.045 to the x. So now I want to find, what is f of 5? 4,000 times 1.045 to the x. This would be pretty hard to do without a calculator because I need to take 1.045 to the, error. That doesn't need to be an x, that's a 5. Okay, 4.045 to the x. So 4,000 times 1.045 to the 5 means I get, we're going to round, so I'm going to use the approximately symbol. That's approximately 4984. Since we're dealing money, we'll do 2 decimal places, 73. So I will have approximately $4,984.73. Okay, so again, we're investing money and we're getting interest rates. So they're paying us to invest our money. So we made more money. We made about $900 here. Okay, so now it says, suppose the interest rate doubles. Does the value of the investment after 5 years double as well? Well, I don't know. Let's try it. If the rate doubles, so the rate was 4.5, doubling means twice as big. So now my rate would be 9%, 4.5 times 2, right? 4.5, double, that'd be 9%. So I'm now at 9%, which is 9 per 100, which is 0.09. So let's call this function g of x, give it a different name. So it'd be 4,000 times 1 plus 0.09, so 1.09 to the x. So now we want to find what's g of 5. 4,000 times 1.09 to the 5th. All right, let's try it. 4,000 times 1.09 to the 5th. 6,154. Wow, I made good money. 49, so that'd be 50. Okay. Does the value of the investment after 5 years double as well? Okay. No. Well, first of all, for the investment to double, well, the investment was $4,000. For it to double, that would be like $8,000. No, but I think what we're looking at is what happens to, like, does the amount of money I make double? If we look at this one and we subtract that $4,000 off, I made $984.73. That's how much money I made. If I take $4,000 off of this guy, I made $2,154.50. The amount of money I got out of it more than doubled, didn't it? $2,154. If we take that, because if I take that 984.73 and double it, I get 19. So I made $2,000. So I made more than double the amount of money by my investment. By my interest rate doubling, the amount of money I made. Now, the value of the investment didn't double, okay? The value of the investment is $4,000. For that to double of 4,000 is 8,000. That didn't double. But the amount of money I made more than doubled. Interest is an interesting thing, okay? It doesn't work always how we think it would, okay? All right, so we have this very last task. We have the number of bacteria cells in a lab culture is growing exponentially. So exponentially meaning it's going to fit the exponential function. How many cells will there be in 10 days? We don't know the rate. Don't know the rate. So our exponential growth model with 1 plus r doesn't really work here. But we do know it's growing exponentially, which we know an exponential function is a times b to the x. I know it needs to fit this pattern. Okay. And I know a bunch of ordered pairs. I know when I input a 0, I get out a 36. So when my x is 0, my output is 36. When my x is 1, my output is 108, so forth and so on. So I'm going to go ahead and use this model and plug in what we know. When I plug in a 0, a times b to the 0, I get out a 36. Okay. I know when I plug in a 1, a times b to the 1, I get out a 108. So if I look at this guy right here, b to the 0 is 1. A times 1 equals 36. I know my a value now. I know my A value is 36. So now over here, B to the 1 is just B. A times B is 108. I know A is 36. I know that is 36. So I know 36 times B is 108. We're just plugging in the stuff that we know. If I divide both sides by 36, I know my base. My base is 108 divided by 36. 3. Hey, that's a nice number. My base is 3. So I now know a function for this. My f of x equals a, which is 36, times b, which is 3 to the x. That's just me plugging it back up into here. Basically, I just needed to find what my a and my b were, which these ordered pairs over here helped me do it. So there's my function, 36 times 3 to the x. How many cells will there be in 10 days? Well, if this is day 1, if this is day 1, 0, 1, 2, 3, I'm wondering what is day 10? Basically, if my input, this is my input. If my input is 10, that's my x. So I need to find what is f of 10. So 36 times 3 to the 10th. Okay, 36 times 3 to the 10th is, wow, 2125764. 2,125,000, which again, this is growing really fast. And look, day 3 already had 972. So it's multiplying by 3 each time because the base is 3. So it does make sense. By 10, it would have that many. So it has that many cells. Okay.